very intense. Today we have to start and finish to talk about photoelectric effect. And tomorrow we have to start and finish to talk about Bohr's model of a hydrogen atom, which includes in part statement that an electron orbiting a proton can have only specific trajectories with only specific radius. An atom can only have specific energies, and when, for example, light encounters an atom can absorb that energy and increase its energy, but then it can release that energy back in the form of light, and that light might be traveling away. And on Wednesday we have to start and finish the discussion about the structure of atomic nucleus, which you know from chemistry very well is built from protons and neutrons. But what you may not know is if we measure the mass of a nucleus and then we measure mass of individual protons and neutrons it's made of, we will see the difference, and that difference is directly related to the amount of energy used to keep them together in a nucleus. We will talk about that. And finally, we will have to talk about nuclear reactions, actually, including a radioactive decay. If you look at the periodic table, many elements actually unstable, which means they can't live forever. Eventually they explode, or we say decay, and for different materials it may take different amount of time before they decay. Some are very long living things, some very short living things. Doesn't really matter. What we know is the intensity of the radioactivity, the number of decays happening every second, of course, is directly proportional to the number of radioactive atoms. More atoms, more intensity; less atoms, less intensity. And those numbers exponentially decrease in time. They can't ever increase, they only decrease. And for each element, there is always a specific time interval, time period. If we wait this time, we see that exactly half of the initial amount has left undecayed. And well, this is everything important to know, which can help you to begin the final journey into your homework. But before that, of course, we have to finish what we started. And of course, you know me, I've got a question to you. This is literally the last picture we saw on Friday before we left this room. It shows the orientation of the electromagnetic wave before it traveling through the first polarizer. Then it shows the transmission axis of the first polarizer. Then it shows the transmission axis of the second polarizer. And of course, we can always draw a picture. So light is approaching the first polarizer. That's what we call the initial intensity. After the first polarizer, light should have a different brightness, different intensity, and the question is about this relationship between these two numbers. It could have been the answer number 8, but it also could have been the answer number 7 or 6 or 5, etc., etc. So in this particular question, for specific reason, I use numbering backwards, because there is also number 9 answer, which says none of the above. It's always on the list. So, of course, the light will be traveling through the second polarizer, and there will be an additional transition, an addition, bless you, relationship, and the intensity after the second polarizer we could have called second or final. So yeah, well, now I have plenty of time. I don't have to rush. See, the difference between this picture and this picture is simple. We can very clearly see all the angles. In this picture, how would I show the angles? It's very hard. I, of course, could draw something like this, like electric field and transmission axis number 1 and transmission axis number 2, but it's really not very informative. But if we imagine we look at this set of polarizers, the eye actually sees all those directions. And light is blinding us, but we can close our eyes and imagine what we see. Those will be the directions. Well, can it be the answer number 8? What do you think? Can the answer number 8 be correct for this situation? You should say it. Only I can see your movement. So, yes? So if the question is, can the answer number 8 be correct? The answer to this question is no. Next question, why? Then you said correctly, because the light is already polarized. So if the light would have been unpolarized, like it was on Friday, we could have used this only for unpolarized light. If light is polarized, we have to use the Malice's law, but to use it correctly, we have to use a correct angle, and it depends, of course, on the exact literal application of a definition. The angle must be measured between transmission axis and direction of polarization of light, which is, in this situation, between this direction and that direction. This is the angle we have to use. That's it. If we know the definition and apply it correctly, that angle is supposed to be equal to -50 minus 20 degrees, which is 30. And the next angle will be, so now we can write I final should be equal to I1 times cosine squared of theta. That's a new theta, so probably a good idea to add a symbol. And that's going to be between transmission axis number 2 and the new direction of polarization of light, which now supposed to be the same as transmission axis number 1, because that's what a polarizer does. It does two things. It changes the intensity and rotates electric field. So after the polarizer, electric field preserves preserves the direction of transmission axis. So this angle is supposed to be equal to now, actually, wrong direction. So that's transmission axis number 1. It's 50, 20, again 30. Again 30 degrees, right? So from between 20 and 50, and then between 50 and 20. Well, it's a coincidence. Okay, I had a slide. So we have to use 30 degrees twice. Moving on. It's very important to know the definition. How do we measure that angle? Transmission axis and electric field. Well, this is probably 6th or 7th time we ask the same question. We know it's neither or both, depending on your philosophical preference. So historically, the dominant theory at first was, for many years, was the particle theory of light. Sir Isaac Newton was number 1 figure who developed that theory to explain shadows, reflection, refraction, and some other phenomena. People knew at the time the difference between how particles and waves behave in different situations. Yeah. For example, waves do not form clear shadow if wavelength and the obstacle have similar size, but particles never bend beyond the obstacle. And if we compare the behavior between waves and particles in an experiment like this, we should see the collection of particles reaching the screen right across each slit, but waves behave differently, right? However, at the time, no one applied the wave-like theory to light until this person, Thomas Young, was a physician, not a physicist. Physics was his hobby. And of course, a physician, Newton, for almost 20 years, no one was paying attention to his paper. Only much later, in France, French people, revolutionary people, his ideas picked up, and well, you would think 20 years is too long of a time in science, right? But well, people can be arrogant, even scientists, even in physics. Well, the most arrogant people, not scientists, not even politicians. The most arrogant people who made millions and billions on their own. They think if they know how to make money, they know everything about everything, including education. All right, I gotta rise this, low this. No, it's too low. I've had some face-to-face with those people. Their views on education just laughable. Oops. All right. Come on. That's too much. Oh, come on. It was much better a couple of days ago. Oops. What's happening there? That's what I try to achieve. The classical experiment has name Argus. Or that doesn't make any sense. The beam should be even higher. All right. Let's see if I can make it work today. I need to lower it. Where is it? Here. Maybe I need the lens today. Now I lost my ball. Okay. The picture you saw on the screen actually was done a couple of years ago. I made it. That's why I usually don't do this experiment. It takes a lot of time to make adjustments. Hmm? I was aiming at the shadow, yeah, exactly. I was, let's see. Come on, work. Okay, it does work. Now let's see if this camera will pick it up. All I need is one good shot. One more minute and I'm done, no matter what. Well, I see it. I can touch it. Not sure if you see it. Here. Well, my thumbs up. We have to move on. That's an enlarged picture of never watch, aim a laser into your eye. And you will be using lasers today and tomorrow in labs, so be very, very careful. Not green one, red one. Red is not as dangerous as green, but still. Well, those types of experiments changed the mind of physicists. So Fresnel, Huygens convinced everybody that light is a wave, not particles. And after that, for decades, people thought that light is a wave. And even some experiments like refraction have been explained using the wave theory of light. That's why people abandoned the particle theory of light completely. Yeah. You see a wave front. It is approaching the interface between two media, and new waves being generated. And because they travel in different media with different speed, new fronts, you see, they travel at different angle, and this will be the direction of, well, reflected wave, and this will be the direction of refracted wave, and we can do a very simple mathematics and derive the Snell's law. So we don't have to think about light as a set of particles anymore for anything. There was one more phenomenon which Newton had hard time to explain, the dispersion. So I'm asking this question for you because I need a couple of minutes to prepare this experiment. So what we have here is a prism. Well, you know how it looks like. This prism is made of material with very high index of refraction. That's not glass, that's a crystal. So we have only one of those, very old, very bitten. And here I have a slit. Light travels through this lens toward the screen. What I want to do, I want to use this prism to bend it and to create a spectrum, a rainbow. Of course, we only have two options. And of course, you've seen before what should be happening. And Let's see if this will work better than the previous experiment. Prism. I've never dropped it once. Other people did many times. So what I want light travels like this. So we know light is getting bent toward the base. My base is here. So that's how I want to do it. Yep. The rainbow. So this is the base. Well, this is the base. Light was traveling like this. So we can see that the red light actually bent less than the blue one. The blue one bent more. Well, this is happening because the blue has shorter wavelength, so it interacts kind of more intense with charges, and that affects the angle of refraction. This phenomenon has a name of dispersion. Normally, the index of refraction depends on the wavelength in such a way, so when wavelength slightly increases, the index of refraction slightly decreases. And if we apply the Snell's law to do different colors, we get this. And if you'll see a rainbow, that's actually a very complicated phenomenon because it involves, well, imagine those are tiny water droplets floating in air. So light experiences, we see light experiencing total internal reflection, refraction, dispersion, and then our lens, our eye lens, converges light on retina. And there is a difference between making a spectrum using a prism and making a spectrum using a diffraction grating. We saw that before. See? In the diffraction grating, red light affects the most, the blue light the least. In the prism, that's the opposite. Well, when people have become very, very convinced that light is a wave, about 100 years ago, new experiments started emerging, which either were very hard to explain using wave theory of light, or impossible to explain using wave theory of light. For example, it was very difficult to actually calculate how much pressure light would exert on a mirror. If we use a particle theory of light, that's obvious. Particles, they bounce off a mirror and they exert a force. We can calculate that force like we did for molecules in air. And some people have been suggesting using this for space traveling. If you have a huge space sail, light can push on it and make it move. At first, of course, very, very slowly, but over a long period of time, it's going to travel faster and faster and faster and faster. So fast it can leave the solar system and just fly away, never come back. Radiation, the phenomenon which we use every day because radiation happens everywhere. Sun, burning fuel. People couldn't explain how much energy is being radiated. People couldn't explain the spectrum they observed using wave theory of light. And the most important phenomenon for today, photoelectric effect. A photoelectric effect is actually a very simple phenomenon. You have light, you shine that light on a conductive plate, copper, zinc, gold, platinum, and you can see that sometimes under certain circumstances that light ejects electrons. You can apply electric field to move those electrons, to collect them, to see what's happening to them, to measure how many electrons traveling per second. That's what we call electric current. To measure energy of those electrons. And people have been trying to apply the wave theory of light to explain that phenomenon. According to wave theory of light, that should be happening. For example, if we shine brighter and brighter light, brightness means intensity. Intensity means amplitude of electric field. If we increase amplitude of electric field, we should exert stronger force. That should lead to more energetic electrons. That doesn't happen. It just doesn't happen. So the experiments contradicted completely. The conclusions derived from the wave theory of light. Again, let's try one more experiment. So I've been keeping this equipment dry because moisture would not allow to charge the electroscope. So let's hope it's dry enough. This plate is made of zinc. Well, first, every time just before the experiment, everyone, you, if you want to do the experiment, have to clean it up because dirt makes harder for electrons to be ejected. So we just want to decrease the barrier as much as possible. All right, let's hope it's clean. Now, the crucial moment. Please work. All right, there's some charge. Now I just want to transfer this charge from this flamingo to the zinc plate. Okay. Now let's see if this is today, this charge is actually negative. Yep. All right. Let's see it one more time with a close-up. So the most valuable member of physics department. Even more valuable. Well, what's going to happen? Nothing. That's a regular visible light. This is a UV lamp. You can see bluish. So it works. And if I apply ultraviolet light, that's it. All charge disappears. UV light is energetic enough to eject all extra electrons I put on it. That's it. And I can do it again and again and again. The result will be the same. And of course, in a lab setup, I could have used different type of UV, so I could manage the frequency of light I use. By the way, now, of course, we have much more sensitive elements. Yeah. This should work. Yep. This is a prototype of a solar panel. Yeah. The material is such that even regular light is enough to generate electric current. And electric current makes this motor work. And that's what a photoelectric effect is about. two people provided significant impact on the theory. First, Max Planck, he suggested, for a different reason actually, to explain radiation energy spectrum. He suggested that light actually can be emitted or absorbed only in portions, which already contradicts wave theory. And Einstein moved it a step ahead. He said light is composed of tiny particles, photons. If we have billions of photons traveling in space, they start to behave like a wave. But each individual photon travels like a particle and has an energy which is directly proportional to the frequency of that wave they compose. And the coefficient is a fixed number introduced by Max Planck, Planck's constant. And now, with this new idea, physicists had to invent new relationships which would relate properties related to particles and properties related to waves. To describe particles, we use a momentum, location, speed, energy, including kinetic energy. To describe waves, we use frequencies, wavelength, energy. So they had to invent a completely new set of equations. And they did. For example, well, for us today, well, this is not a new equation. Yeah, this is a very well known old-fashioned relationship between speed of wave, frequency of wave, wavelength. But there is another new equation which relates the energy of that single light particle and the frequency of the wave. And well, first, let's practice in using those equations. (620 nanometers). That's the number. Max Planck's constant is about 6.6 times 10 to the negative 34 a joule times a second. That's the standard unit using international system of units. And well, speed of light equals 3 times 10 to the 8th meters per second, and speed of light is related to 1, 2, 3, 4, 5. Speed of light is related to frequency and wavelength. So what can we do? Well, first we can use the equation number 5 to relate frequency with the wavelength. Now we can use the equation number 1 to get the energy. Now we can use the numbers. Now you can use a calculator, hence, and calculate this energy. And since we've been using international system of units for everything, we should get joules. And I believe I have it found. Please just take a minute, just calculate. It's a handy practice, you know, handy exercise. So 6.6 times. When you write what you want to calculate, of course, you are much more accurate than I am, right? You know which dot represents a decimal point and which dot represents a multiplication symbol, right? So anyone? Yes?
3.19 times 10.
Exactly. Do you recognize this power of 10? 10 to the negative 19th. Have we seen it before? Yes. Coulomb's charge of an electron. So this is one of the reasons people have invented a new unit for measuring energy. They call it an electron volt. This is a conversion factor between what we call electron volt and a joule. 1 electron volt is equal to 1.6 times 10 to the negative 19th joules. That's official definition. If we take an electron, release it from rest, doesn't have to be, but it's easier, release it from rest, and it travels through 1 volt, that's the amount of energy it gains. That's it. So if it travels through 1 volt potential difference, it gains 1.6 times 10 to the negative 19 joules, or 1 electron volt. If it travels through 2 volt potential difference, it gains energy of 2 electron volts, etc., etc. And now we can calculate the same energy using electron volts. All we have to do is just use the conversion factor. That's the energy in joules. We need to divide it by the conversion factor. And now we can see why this unit is very convenient. We get simple, manageable numbers, 2 electron volts. That's the energy of that particular photon. So if you have a wave with billions of billions photons and the wavelength of that wave is equal to 620 nanometers, each photon carries 2 electron volts of energy. Now, question. We take an electron, release it from rest, let it go, let it travel through the potential difference of 3 kilovolts. What's going to be the final energy of that electron? This is something I would like to take a look at. So I got to resend my credentials. Now I have to go to question number 4, 3. Oh, nice, good distributions. Number 4, just 2 people answered so far, according to the Webassign. So let's wait a little bit longer. We let it go from rest. Initial kinetic energy is 0. The energy it gains due to work done by electric field is equal to, survey says. I wonder if we would survey 100 people on the street with this question, what would they say? Well, this is not a mathematical question. This is an arithmetical question. 1 volt gives the gain of 1 electron volt. 2 volts give the gain of 2 electron volts. 3 volts gives the gain of 3 electron volts. 3 kilovolts gives the gain of energy 3 kilo electron volts. That's why we use them. Kilo means 1000 volts. Of course, we could do some math and calculate it. But why would we? Now we just need to use everything we said to get a Nobel Prize. Einstein did, why wouldn't we? We just have to repeat what he said. And he said, if we have one photon traveling in space and colliding with an electron, we know everything about collisions actually. The law of conservation of momentum would give us a Compton effect. We're not going to talk about this, but law of conservation of energy is actually very simple. So if this photon, this particle, has a certain energy, and what might happen to that energy? Well, first of all, this electron is inside certain material, so it's being held inside by a nucleus or something else. So first, we have to bring it to the surface, and then we have to push it above the surface. That requires a certain amount of work. So that's one part of energy spent by the photon. But if the photon energy is actually greater than that amount required to bring the electron just above the surface, what else might happen? Well, the rest of the energy can go to speeding up the electron. So it might travel away from that surface. And that amount of energy can be described by old-fashioned, well-known kinetic energy. So the energy of a photon can be used. Well, technically, some electrons might lose more energy than this minimum number required to eject it. So some electrons might have kinetic energy less than this. So this only tells us the maximum amount for kinetic energy of the electrons ejected of a plate. And the energy of a single photon is related to the frequency of a wave. And this is the Einstein's law for the photoelectric effect. That's it. I saw it first time when I was in 9th grade, but it was a different country. People also write it like this: maximum kinetic energy of a photoelectron ejected of a plate should be equal to this. This number depends on the material. It has a name, a binding energy or work function of that material has been measured, bless you, for all materials. For zinc, it's 4.3 electron volts, for example. So kinetic energy cannot be negative, which means not every possible frequency of light can work. Kinetic energy must be greater than 0, or the critical value of kinetic energy is 0, which means there is that critical frequency which we can solve, which we can find from solving this equation. The critical frequency for that particular material should be equal to this ratio. So just an example of different work functions for many, many different materials. Of course, you can just Google any work function for any material. And the question, if you look at this table, let's say we have light shining on zinc plate, and photon energy is 5 electron volts. Should we or shouldn't we observe the electrons ejected by that light from the plate? Zinc. So the type of mental work we're doing right now is search. Found. Number. So pick your answer. Question number 5. Enter it. There is an applet which I find very handy to play with. Here you can try to shine light with different frequencies. If this is a filter, so right now this is a yellow filter, so it only transmits light with given wavelength, 578 nanometers. And the material coating here is cesium. So what we see, well, this is the ammeter. It measures electric current. It measures electric current in this circuit. Ignore everything else, doesn't really matter. If we observe electric current is not zero, that means these photons eject electrons, and those electrons, well, on average, they travel chaotically in all directions, this, but eventually they reach the opposite electrode, get picked up by wires, and travel through the ammeter. Photoelectric effect does happen. What can I change? Well, material, potassium, no photoelectric effect. Yellow photons, not energetic enough. We can try ultraviolet. We can see that ultraviolet light is energetic enough to generate photoelectrons. Now, we can, well, if we use slang, kill it. Electrons travel from this electrode to opposite electrode, but if I apply electric field in opposite direction to the motion, so they will be attracted. Well, electric field actually should point electrons negative, electric field should point in the same direction, but it will exert a force in opposite direction, so they will be tracked back. So if my electric field is not strong enough, electric current still is not zero. But if I start gradually increase the voltage, less and less electrons reach the opposite electrode. Only those which travels as fast as possible with maximum kinetic energy. So eventually I can reach the potential when there is no electric current at all. So even the most energetic electrons now can't reach the opposite electrode. Because what? Because electric field brings all them back. And to do that, electric field does work. How do we calculate work done by electric field on a charge? Anybody? Problem number 3, exam number 2. Oh, well. problem number 3, exam number 2. It equals to charge times potential difference. And this is the potential difference. We actually read volts. 1.3 volts. That amount of kinetic energy electrons lose to the electric field. So 1.3 volts is equal to what amount of energy in electron volts? (1.3 electron volts). So this number we read immediately tells us maximum kinetic energy of electrons. And then we can choose different frequency and repeat experiment. This experiment. So yes, and now we know how to explain different relationships. If we measure electric current with a fixed frequency, the frequency is fixed, but we make the light brighter and brighter and brighter and brighter. Now we say we just make more and more and more photons colliding with the plate. Each photon collides with a single electron. So increasing the number of photons, we are increasing the number of electrons ejected. That's it. No light at all, no electrons. So this graph should start from 0. 0 intensity, 0 current. If we increase the brightness, of course, we increase the number of photons hitting the plate, we increase the number of electrons ejected of a plate. And wave theory of light couldn't explain this, but the particle theory of light explains it like that. Very natural. We just have to say that well, first of all, I can't not mention that double negative. You got to pay attention not to letters. You got to pay attention to what they mean. This means the intensity of light, brightness, basically, measured in joules per meter squared per second. That means electric current measured by this ammeter. Now, what about stopping potential or retarding potential we saw in the applet? Well, again, let's have first fixed frequency. We observe electric current. The electric current is not 0, even if potential is 0. If we increase potential, making electrons travel faster and faster, of course we see higher and higher current. But if we switch potential in opposite direction and start increasing electric current, eventually should become equal to 0. This value, that critical value of potential, when it happens, has a name: retarding potential, stopping potential. It stops the effect. And what can we do? Well, we can apply the law of conservation of energy. Work done by electric field should be equal to maximum kinetic energy of those electrons ejected by light. And we can plot the graph for different frequencies. For a yellow, frequency number 1, kinetic energy number 1. What's next? Green, blue, ultraviolet. And then we can draw a line. Why should it be a straight line? Well, first of all, we can actually derive a mathematical equation for this line, as as we did it in geometry work function plus. That's the Einstein's law for photoelectric effect. We just have to solve it again for kinetic energy, for the maximum kinetic energy, which will be equal to. And this actually looks exactly like old-fashioned linear equation. How do we call this coefficient? How do we call this coefficient? Slope. How do we call this coefficient? Thank you. So this graph tells us exactly how to calculate work function, because it's, well, if we go like this will be y-intercept, which is equal to this. So we just read this number, that's going to be work function, well, times -1. And the slope should be equal to the Planck's constant, which is, I don't know, I personally find very, very beautiful. When you can calculate the value of a fundamental physical quantity using very simple reasoning, that is amazing. Switch to physics, everyone. You will experience this feeling often. Well, so now actually we know everything about photoelectric effect. Every single thing. So if the words weren't clear enough, you can read. These slides represent word by word everything I said, including the graphs. Well, we're going to solve a couple of more problems, and one of these problems, kind of backwards to what we said and what we solved. Let's say we have light traveling in space, and the photon energy equals 2 electron volts. And our immediate goal is to calculate the frequency of that wave. What can we use? Well, the set of equations is the same. Planck's equation for an energy of a single photon, and a standard equation which relates speed of a wave, in this situation speed of light, wavelength and frequency, and the frequency is supposed to be equal to this divided by that, and what are we looking for? Oh, we don't even need this. Frequency will be equal to energy divided by constant. The energy is equal to 2 electron volts, and Planck's constant is about 6.6 times 10 to the negative 34, and that actually requires a conversion factor we've used before. 2 electron volts in joules, 1.6 times 10 to the negative 19th, 6.6 times 10 to the negative 34th. Now, what people do, they use electron volts and then invent a new constant, which is 6.6 times 10 to the negative 34th divided by 1.6 times 10 to the negative 19th. This is actually Planck's constant, but not in joules times second, in electron volts times second. And well, someone should calculate it. 6.6 times 10 to the negative 34 divided by 1.6, negative 19. I've got 4.1253 times 10 to the negative 15. Actually, it's more like 4.14 if we use more accurate number for actual Planck's constant. Electron volts times seconds. So now the frequency will be equal to 2 divided by 4.113 times 10 to the negative 15th. We bring it over, makes it 10 to the positive 15th. So this is kind of shortcut you can use. If you want to, you don't have to. So that's going to be around less than 0.5. 0.48, yeah. And in this particular topic, people use some shortcuts, and you don't have to, but you can find them on the equation sheet, and it's up to you if you want to always use international system of units, or you want to make yourself familiar with using shortcuts, electron volts, and other constants. Calculate the wavelength. Well, now we make a step further. The wavelength equals the speed of light over frequency, and the frequency equals photon energy over Planck's constant, and that gives wavelength is equal to speed of light times constant divided by energy. And now I'm going to say practice at home. You know that if I put 14 dots, that means practice at home. And I did. I practiced. Oops, where is it? Yep, I practiced at home. This is just another application of everything we've said. That is the speed of light. This is the energy in electron volts. And this is Planck's constant in electron volts times seconds. So if you multiply these two numbers, we get a new shortcut. We can calculate the wavelength in nanometers immediately if we use this expression. Of course, we don't have to. We can always use actual values with actual units. But it's just much faster to use this shortcut. This is a fixed number. And if you know the energy in electron volts, 1240 over 2, 620 nanometers. And we can use this shortcut backwards. If we know the wavelength in nanometers, what do we do to calculate the photon energy? Same equation. Same constant, electron volts per nanometers, times nanometers. And well, now we can actually solve a problem. Iron has a work function or binding energy. So that's what we call W naught. Of course, it is always given in electron volts. And of course, we can always convert it into joules. And of course, we can calculate everything. For example, we can calculate what supposed to be that critical frequency of light which is sufficient for ejecting photoelectrons, which begins the photoelectric effect. And if the frequency of light is below the critical, nothing is happening. If the frequency of light is above the critical, of course, electrons are ejected and actually travel in space, having some speed. So, first equation, which we need to write for a photoelectric effect, is the Einstein's law for photoelectric effect. This number is equal to electron volts. Now, critical frequency means no kinetic energy. So, that's it. That's the critical energy photons need in order to begin the photoelectric effect to happen. And well, what can we do? If we know energy, we can calculate frequency, we can calculate wavelength. Actually, let's do wavelength first. I like the wavelength first. It equals 1240 divided by 4.5. That's not just any wavelength. That's a specific critical. If light has a longer wavelength, nothing will happen. We need shorter wavelength, higher frequency in order to light to eject electrons. So 1240 over 4.5. 1240 over 4.5. 275 nanometers. We know the visible spectrum lies between about 400 nanometers and 700 nanometers. So this light doesn't belong to visible spectrum. It's actually like ultraviolet light or some. Yeah. Now we can get the frequency. Frequency should be equal to speed of light divided by wavelength. And now actually I prefer using International System of Units because it's very easy to convert nanometers in a number. It's just -9. That's a plus. I've been thinking about nano, yeah. So 3, 10, 8 plus 9, 275. .011, 17. So people usually end up like 14 or 15. So if I move 1, 2, 3, or 11, 14. Something like that. Oh, the next number tells us, so 1.1 times 10 to 15th. So now we can compare this number with the next number. The next number is higher. So light with this frequency definitely definitely will eject photoelectrons. And of course, now we can calculate the kinetic energy of those electrons. So the law says but that is not how I want to use it. We know the frequency is 1.5 times 10 to the 15th. So we have two different approaches. What my immediate goal actually is to calculate the photon energy in electron volts, because I know this number in electron volts, 4.5 electron volts. So that's what I want to use as a unit of energy. So we have two options to do that. Number one, we can use this equation, but we can use the value of the Planck's constant in electron volts times a second, which has been calculated before. .4 times negative 14. And the frequency is 1.5 and 15th. So this is going to be 6 electron volts. So maximum kinetic energy of photoelectrons will be equal to 6 minus 4.5, 1.5 electron volts. And now if we really want to, we can calculate the same kinetic energy in joules. 1.5 electron volts times 1.6 times 10 to the negative 19th joules per electron volt. Why do we need it? Well, sometimes we may need to calculate speed. And in that case, we would have to use the mass of a single electron, about 9 times 10 to the negative 31st speed squared over 2. So speed would have been equal to 1.5 times 1.6 times 10 to the negative 19 times 2 divided by 9 times 10 to the negative 31st and square root of that. And that would give us meters per second. And of course, I've got the slides with calculations and with a shortcut. And now, again, this is something you have known already from chemistry. At the time, in physics, two competing theories have been presented, studied. Thomson, who actually discovered electrons, thought that an atom is like a cloud, positively charged cloud, with electrons sitting inside. But the Rutherford experiment, which you have heard, proved this theory to be wrong. An experiment was kind of neat. You had a radioactive uranium and tiny particles. At the time, they've been called alpha particles, were ejected and traveling toward a thin foil of gold. Well, probably if they had thick foil of gold, they wouldn't be doing anything. But they only had thin foil of gold. So they, well, actually not Rutherford, his grad students discovered that some of those particles have been bounced almost 180 degrees back. That would never happen if the atom would have been a cloud. They would be deflected, but still they all would get through. And the Rutherford experiment gave a proof that a different model, a solar model of atom, was correct. So the nucleus is a tiny, but very, very heavy, very, very dense particle, electrons moving around like planets about the sun. And when very fast, very energetic alpha particle collides with a very dense, very solid nucleus, they bounce back. And the simplest atom, of course, has only one positive charge in the middle and one negative charge orbiting, the hydrogen. And for the hydrogen atom, the equation which we should use has been used already, has been written already before. It's a standard combination of Coulomb's law, centripetal acceleration, and Newton's law. We've been using that equation before. And we can solve it for anything we want to. For example, for kinetic energy, that is a kinetic energy of an electron orbiting the proton. A potential energy should be equal to a potential energy for two charges. Total energy of atom should be equal to kinetic plus potential. Coulomb's constant squared 2r. Coulomb's constant charge, elementary charge squared r. So what we have is 1/2 minus 1. First of all, as for any bound system, total energy is always negative. The problem with this is that according to the classical theory, as we saw it in an applet with an electron moving up and down, when electron has acceleration, it has to excite electromagnetic wave, and that wave should take away all the energy eventually, actually very quickly. In the fraction of a second, atoms should implode and disappear, all atoms, not just hydrogen. So we wouldn't be able to live longer than 10 to the -8th of a second. Nothing would exists any longer. But we exist. Yes? Okay, good. So classical theory couldn't explain the existence of atoms. The ideas to fix came from, well, combination of particle and wave theory of light. If light may be a combination of particles and waves, why particles can be a combination of particle and waves? And turns out they can. This is a classical experiment has a name. Electron diffraction, not light diffraction. Electron diffraction. Well, you can see it here. Ooh. Where is it? Where is it? Where is it? Where is it? Ah, too bright. I hate this room. You can see circles. Do you? This is a diffraction pattern. How do I know those electrons? Well, I can deflect them by using a magnet, using my left hand. So, what is happening? Turns out electron is a particle and a wave in a way. A single electron, when it hits a screen, of course, hits it at a specific location, like a regular particle. However, oops, if we have many, many, many of those electrons traveling to a screen, the pattern emerges. The more electrons reach the screen, the better we see the pattern fringes. We actually can take a ruler, measure distance, and since we're managing voltage, we can manage energy and speed of the electrons. And turns out that this wave pattern is related to a momentum with this simple expression. H, again, is Planck's constant. And first, the idea of this relationship has been offered in dissertation, PhD thesis of this guy. He was very young. People didn't really understand his thesis at the time, but then they used it. Niels Bohr said, well, if atoms exist, probably there's a reason for that. So he made an assumption, a stroke of a genius. He said, electrons can have only those orbits where electron wavelength generates a standing wave. That's it. And this simple idea led to, well, what we call now quantum mechanics. In quantum world, almost all variables have only discrete values. Only certain values are allowed. Most values are restricted. And now we're done. I'll keep you in suspense. But now you can solve, I would say, probably about 80% of homework 3 part 3 and even homework 3 part 3 problems. So you should start doing it right now. Like just leaving the room and just sit down and start doing the homework. Morning. This goes. I just want to take this off and I want to, oops, where's the ball?
Colors.
And I want to take this